second Galaxies session of our meeting. I should cover a good fraction of what's interesting about the universe, I think. And so I think, yeah, without further ado, it's already a few minutes past 2. We're going to start with our first speaker, Thomas Quinn. I'll be trying to keep people to their allotted time here of 15 minutes, so that hopefully there's a few time for interesting questions afterwards.
So thank you. It's great to be back. So I think most of you know I'm part of this Embody shop where we do embody simulations of both solar system and cosmology and galaxies. And I'm going to talk about both in this talk. This is work actually by graduate students, Nate Cave and Mark Oscar. I'm mostly doing cheerleading, but I think it's a great project. This is a plot that I made when I was here. Scott and I and Martin. And part of the reason it's demonstrated, so we have sort of time scale to move a comet around based as a function of the comet's centimeter axis. I think it was Scott that pointed out that it's not only the individual stars, but it's the tide of the galaxy as a whole that torques comets out of the planetary system once they get a sufficiently large centimeter axis. And it's the interplay between this torquing timescale and the diffusion timescale caused by interactions with the planets that determines the structure of the four-cloud comets. So one could ask, what if the tidal torque changed? Generally, when people think about this, well, they think of the sun moving in a circular orbit around our galaxy. So you've got maybe passages in and out of the disk plane, perhaps passages through spiral arms. But we know the spiral arms really, although they look spectacular, really aren't that big a change in density. So the standard model is that this tidal torque has been roughly constant over the age of the solar system. However, we know that over the age of the galaxy, and talking about cosmology, the galaxy actually formed and grew over cosmic time. And so what we want to do is see what the growth of the galaxy, how that affects the Oort cloud. So we have these called cosmologically motivated, they're still isolated galaxies, where we have a modified NFW profile with hot gas, and if we let this thing go, the gas will cool and collapse into a disk. The disk, well, these are just the stars, with the blue being younger stars, and they turn red as they grow old. And the gas keeps cooling onto it, so you keep sustaining these spiral arms and growing the galactic disk. So what does that look like in the end? This is to show that we've got enough resolution that we actually have a thin plus thick disk in these, and we match a number of other properties of our local neighborhood in terms of dynamics. Overall, the model we get out, well, it's a little, rotation velocity is a little bit high, but comparable velocity dispersion to the Milky Way, comparable scale length, comparable scale height of the disk, and comparable midplane density. But the surprising thing, and there it is, the surprising thing we found from these simulations is that if we looked in the outer parts of the simulation, and this is a plot of the probability, given that you find a star at some radius, from whence did it form? Or where did it form to get to that radius? And so the surprising thing is if we look in the outer parts of this disk, the bulk of the stars that are in the outer parts of the disk form significantly closer in. And indeed, even at 8 kiloparsecs, see that the majority of the stars, over 90% of the stars, form interior to the 8 kiloparsecs and migrated outward. We think we understand it. Selwood and Binney proposed this mechanism that if a star is in resonance with a spiral arm, it can migrate outward significantly and still maintain a circular orbit. And these are typical orbits from our simulation. You can see that it hangs around for a while and then there's this sudden migration. And this has interesting implications for our solar neighborhood. First, stars come from elsewhere, but that naturally introduces a spread in the metallicity, age relation, and broadens the metallicity distribution function, whereas if you assume that the stars formed in situ, you have a very peaked metallicity distribution, which does not match observations of the solar neighborhood. So we took this simulation and we looked for solar analogs. So after the simulation had been run for 10 gig years, it sort of settled down. We looked for stars that were roughly 4.5 gig years old, that were roughly 8 kiloparsecs from the galactic center, that were close to the midplane, and had small peculiar velocities, as our sun does. So in roughly circular orbits. And in this particular simulation, 31 of our star particles satisfy this criteria. And looking at the orbits of some of those stars, so here's where we selected them. And so this particular star behaves as we always thought stars like our sun should behave. Stays roughly at 8 kiloparsecs. These wiggles are essentially just the ellipticity of the orbit. But then there were other stars that formed within 4 kiloparsecs of the galactic center, stayed there for a while, and migrated out. So clearly something different might happen to the Oort cloud around this solar analog than around this. Indeed, if you look at sort of sample where the stars were over their history, here's a histogram of their radius distribution. And we find that the median approach to the galactic center is less than 5 kiloparsecs. So over half of these solar analogs at some point were closer than 5 kiloparsecs to the galactic center. And so what we did was, we couldn't integrate it directly, but we took the simulations and we produced outputs at 10 megayear intervals. And in each output, we took the solar analog out and put in a little jack of particles, just 10 parsecs across, so that we could measure the galactic tide. So in all three directions. And when we use that tide as an input to an Oort cloud simulation, we also record so this tide comes from the total matter. We also looked at the stellar density at each output, so that would determine the frequency of stellar encounters, and also the velocity dispersion would determine how fast those stellar encounters occur. You might imagine that in in-body simulation there would be a little bit of noise in calculating that tide. Here's just gives you an estimate of how noisy the tide is. When you look at so this is the gradient of the vertical acceleration as a function of radius normalized by what we have today. And we see that we get some scatter around a nice exponential profile. The profile is actually a little steeper than the scale length of the disk. The scale length is shorter, but that's because the scale length has been growing over the course of the last 4.5 gig years. Okay, so we do our standard Oort cloud simulation, like I did when I was in CITA so many years ago, except with this time-varying galactic tide and stellar encounters. One thing we wanted to look at was the tracking efficiency. How many of the original comets, again some background, we start the comets out in a protoplanetary disk. They get scattered out. What fraction of those actually remain in the Oort cloud? If you look at the simulation after 100 mega years, you see that the trapping efficiency can get quite high when you approach for stars that got close to the galactic center. That is, the tide was able to pull them out of the disk before the interactions with Jupiter scattered them to infinity. This is interesting, except if you actually then followed the simulation for 4.5 gig years, that's the pluses here. So actually the overall trapping efficiency didn't change much, and the dotted lines, the dashed lines are control simulation. That is the sun staying exactly where it is. So not a big change in the trapping efficiency if you look over the entire lifetime of the Oort cloud. One thing that did change is the semi-major axis distribution. That is, if you got close to the galactic center, then the minimum, median, and this is 5 percentile, median, and 95 percentile actually moved in. So, simulations would keep the sun in the same place for the entire history of the solar system actually overestimate what the semi-major axis distribution of our Oort cloud should be. One interesting correlation is with the trapping efficiency is how close it got to the galaxies. So those that approach very close to the time of approach to the galactic center. Those that approach the galactic center early in their life got many comets put into the Oort cloud. Those that encountered the galactic center later had their Oort clouds eroded by the interaction with the galaxy. And then one last trend that we've seen is that the Oort clouds are more isotropic than they would be if the sun stayed at 8 kiloparsecs. But the isotropy radius, the change in radius at which, at some major axis at which the cloud is isotropized, does not change as much as the semi-major axis. That is, the ratio of the mean semi-major axis to the isotropization radius was actually quite large. That is, big changes in semi-major axis, not so much changes in the inclination. And so this is interesting because we have this interesting object which has a rather low inclination, 11 degrees, and yet it's sort of an inner Oort cloud object. It has a semi-major axis of about 500 AU. The diamond, so that's Sedna, its semi-major axis, and perihelion. For a sun in a circular orbit, you have the black diamonds. That is, it's hard to get a few Sedna-like objects. For simulation that has a close approach with the galactic center, those are the blue pluses, and you get many more candidates that have Sedna-like objects. And if you look at the distribution of the inclinations of those green pluses, we get this histogram that easily includes Sedna, which is the dashed line. Hence, these low inclination inner Oort cloud object is more likely if our sun made a close approach to the galactic center. So the interesting thing is that our sun likely did form 2 to 4 kiloparsecs closer than we are today. And just to summarize the implications for the Oort cloud and inner Oort cloud objects, and the last sort of conclusion is it was a lot of fun to finally connect sort of galactic simulations to Oort cloud simulations after all these years.
We have time for some questions.
Do you think the conclusions would change if our galaxy underwent a major merger?
Yeah, so, yes. All right, so, yeah, obviously. So, the cosmological scenario here is that what I started out with would be after the last major merger. So, in a redshift of 2 or 1.5, 2 big galaxies came together, completely virialized with most of the gas in a hot phase, and then subsequent evolution from redshift 1.5 or something like that. Clearly, if we had a major merger at z equal 1/2, then the Milky Way wouldn't look like it is today, is my guess, right?
Did you say anything about the role of interactions in a birth cluster around the star in determining the work time?
Okay, so right, if the if the sun started out close to the galactic center, then the effects would be almost indistinguishable from being formed in a dense cluster. More interesting is if you get closer to the galaxy after you've evolved for a while, because the Oort cloud evolution occurs over 15-year timescales.
I thought it was really interesting that you're finding that the most distant stars can be further in, so the formation radius is the declining function radius. Is it obvious why that should be the case?
Right. So it takes time to get to migrate outward. So the implication is that there really wasn't any star formation out there. And so for a star to get very far out, had to migrate a long time, and therefore it must be older.
So closer, they had a head start.
Yeah.
Stars,
yeah.
Any other questions? Okay. Thanks again, Tom. So our next speaker is current citizen, Dr. Phil Chang. He'll be speaking to us on heavy vortices and protoplanetary disk.
Vortices in protoplanetary disks, and this is work that I've done with who's a postdoc at UC Berkeley, moving to Stanford soon. Okay, so just to give you a brief outline of my talk, first I'm going to motivate why this problem is interesting, like why study basically vortices and heavy vortices in particular in protoplanetary disks. Then I'm going to introduce these ideas of vortices basically as means which we can concentrate solids in protoplanetary disks. Right? I'll talk a little about the methods of calculation. I'll first introduce basically a very simple vortex model, all right? And taking this simple vortex model at equilibrium, I will basically perturb this vortex model using a technique known as Poupet analysis, right? Which is perturbation theory for spatially and periodically varying flows. All right? I'll show the linear calculation. Now I'll show there's 2 regimes of instability. One regime which I call the vortical Rayleigh-Taylor instability, which happens if your vortex has a light core, and one which I call the heavy core instability, which happens obviously when you have a very heavy core. Okay? I'll finally basically point the relevance to planetesimal formation and to give you the 10-second answer that vortices will not be able to concentrate dust to the concentrations needed to form planetesimals. All right? That will be my claim. All right, so planet formation. How does this planet form? Like the leading model is core accretion, and the idea starts out that we have dust. This dust basically conglomerate forming planetesimals. Planetesimals further conglomerate forming cores, and these cores finally accrete material and form planets. All right. Planetesimal formation, this dust to planetesimal formation, happens in 3 stages typically. First, there's dust, micron to centimeter scale, which occurs from collisional sticking of material, dust, right? And then there's a centimeter to 100 meter to maybe 1 kilometer scale, which is questionable. It's not clear actually how planetesimals how basically rocks get to boulders, or very big boulders, right? And finally, for kilometer-sized bodies performing these planet cores, actually, they thought is basically gravity. All right. Now, this intermediate stage, which is centimeter, meter to up to maybe 0.1 to 1 kilometer, this intermediate stage is a major unsolved problem in astrophysics. And the leading candidate, as far as I can tell, right, is basically proposed by Goldreich and Ward, as well as Safran back in the late 60s, early 70s, which is gravitational stability, right? Imagine you have your dust layer, which settles onto the midplane, right? If this dust layer gets sufficiently dense, such that they come close to the Roche criterion, right? This dust layer will basically collapse, undergo gravitational stability, and fragment into a bunch of like small bodies, right? In order for this to happen, right, the minimum mass solar nebula has a Q, a two-ray Q parameter of 20, right? So in order for me to fragment my dust layer, I need an increase of factor of 2,000 in the midplane dust density. 100 from the fact that the dust to gas ratio is assumed to be 100 to 1, and 20 from the fact, or a few tenths of the fact that the two-ray criterion has to be satisfied. Okay? However, there's a problem, right? And this was first pointed out by Rich Schilling or something like that, or what's his name? Okay. I'm terrible with names, terrible. I apologize. All right. And this pointed out by Weishling back in the early 80s that if you have a sufficiently settled dust layer, right? And if you imagine you have this radial pressure gradient, which will naturally occur if you have the heated planetesimal disk, all right? The dust tends to rotate at comparing velocities, while the dust rotate. Well, the dust tends to rotate at comparing velocities, while the gas rotates at slightly sub-comparing velocities. So when you have this dust layer settled to the midplane, this begins to basically push on this gas, and pushing on the gas basically accelerates it up to closer to comparing velocities. But you have basically what ends up happening, you have a vertical shear layer, right? And when the vertical shear layer gets sufficiently fast, you have Kelvin-Helmholtz instability. And the criteria for that is just known as the Richter's criteria. And typically, the people who have studied this problem have found Richter's criteria about a quarter, or unity, in order for this to happen. What this means is that if you assume everything's at marginal stability, right, the dust layer, right, is roughly, the dust density in the midplane layer is roughly equal to the gas density. And this statement is just a statement that if I want to push my gas, all right, to something that's higher than what the gas background velocity is, I better have enough material which is forcing that gas at that mass. Okay? So in order to basically overcome this last bit, basically, the factor of 20 I need in order to form planetesimals, right, I have to increase the dust concentration. And there are two ways of doing this, right, that I know. So both worked on by Andrew Newton, all right? First is the streaming instability, all right? And the way to understand streaming instability is to actually look at a bicycle race, right? Where if you have a pack of people moving along, and you suddenly have crosswinds develop across it, all right? What happens is that you can basically split people up into different columns, right? By having people who block the wind. Same thing happens with dust. A few of these dust particles, overdensity of dust particles, an overdensity of teammates, for instance, right, will basically allow you to generate a draft where all of these like riders or dust particles will just gather behind it, and you get fairly decent concentrations in this manner, right?
What does the police officer on the motorcycle do?
So this is actually a referee. Yeah. I think he's watching for dopers or something like that. Okay, the other way of doing it, right, is to imagine that suppose I decrease the total, suppose I increase the total metallicity, increase the total dust content in my gas, right? Now, what I said earlier was that in order for Kelvin-Helmholtz instability to set in, right, you roughly need the mass of the dust equal the density of dust roughly equal to the density of the gas, right? And what that means is that like I'm starting to push on the gas, and the gas is starting to become turbulent, and this gas is flowing this dust into the atmosphere. But if I increase the metallicity, at some point, all right, I will simply not have enough turbulent motion in the gas to fling everything up. And what we'll end up getting is I'll end up getting an increased concentration of dust in the mid-plane region, right? So for instance, like if I were just having just solar metal, that's this curve right here, basically I get something roughly where the dust density is roughly equal to the gas mid-plane density. But as I increase that amount of solids, basically, from basically, let's say solar to 2 times solar to 3 times solar, I can get actually much larger increase in the mid-plane density than would be possible otherwise, right? So those are 2 ways. But a third way of doing it is to increase the total dust surface density, right? Which can happen if you postulate there are regions in the planetary disk where dust can be concentrated. And one natural way of doing this is to imagine that vortices are one of those regions. So a vortex in the polar planetary disk is a high pressure region, unlike terrestrial vortices like hurricanes or tornadoes, which are low pressure regions, right? Okay, and this will become important in a second. But basically what happens is that if you just look at where the gas is sitting, all right, versus what the dust is sitting, if the coupling is maybe at 10, or coupling, the stopping time is maybe like 1 time the orbital time, well, you find that the dust is basically concentrated into a much smaller region than the gases, right? And what this means is that if you think about it, right, if I force all this dust into the central regions, and in the midplane, the dust is already equal to the gas density, right? This region has the region inside the vortex has a very, very heavy core compared to the outside of the, compared to the background gas. So one can ask, like, are these dense cores stable against perturbations, right? Okay, so let me just introduce a very simple model of a vortex, basically. And a simple model of a vortex is just imagine this ellipse, okay? And this ellipse is basically sitting in the shear sheet, okay? Now, if you look at what the pressure profile looks like, this pressure profile turns out to be somewhat complicated, right? But there's a natural solution for this, right? Which if you set, basically, you say there's no azimuthal pressure gradient, all right? Then you can basically get this go-right Goodman and the Ryan solution, all right? And in this solution is actually very nice because what it says is that the effective gravity, the pressure gradient between ellipse, different ellipses is constant, right? So the pressure drop across each streamline is constant, right? But of course, because the streamline is elliptical, as you move around, the effective gravity changes as a function of time, right? All right. So then you can ask, like, can one perform perturbative analysis when you have a varying flow? Well, the secret is that it's periodic varying, which means that at some point, if you go one rotation period, you come back to the same exact point that you started. So imagine you have a wave vector A, okay, a wave vector at point A, and you just adapt this wave vector across, and you come back to the same point. You can ask several different questions for it, right? Namely, does this wave vector rotate? Does the wave vector increase in amplitude or not, right? And mathematically, what this means is that in this wave vector, there's a secular piece associated with it and a periodic piece associated with it, all right? And one can basically is interested in the behavior of the secular piece. Is it growing in time or is it decaying in time, all right? And so you can break this equation, the shear sheet, down to 2 points. One is basically the evolution due to advection, right? And this looks nasty, but it actually has an analytic solution. And the evolution due to the fact that there could be a zero background density gradient, right? So let's do that calculation, and this is what we find, okay? For light cores, right? So this is basically cores which are basically increasing in density as I move outward, right? So these are light cores. These are heavy cores, all right? This is growth, this is decay, or nothing's happening. And what you will find is for light cores, I always have growth. There's always an instability for light cores, right? And for sufficiently heavy cores, there's an instability in that case as well. Okay, so let's try to understand the physics behind those 2 regimes, right? So the first regime, for light cores, is actually relatively simple, right? Remember, I said the vortices are high pressure regions, which means the pressure gradient points outward, which means the effective gravity is pointing inward. If I have a light core, that means I'm putting heavy stuff on the outside, right? Which is heavy stuff on top of light stuff, right? That is Rayleigh-Taylor unstable, right? And so hence the name for light core instability is the word for Rayleigh-Taylor instability. The second regime is where I put heavy stuff on top of light stuff. And in that regime, that should be perfectly stable. All right? So why does it become unstable? Well, the reason why is because I have a time-varying gravity, right? And if I increase my density gradient to be a sufficiently large value, right? I can basically have the periodic gravity kick it, right? Until I can basically get a sufficiently, until I basically have parametric instability. And that's what this plot is showing here. This is effective gravity as a function of time, right? This is in terms of basically rotation periods, and you get 2 kicks per rotation, which is the 2 points which you cross this main minor axis of the Earth. And this is basically what's happening with the perturbed density. It basically increases with time. Right? So just to ask, what's the relevance for this? Okay, so what happens is that, okay, what I need is a density increase of factor 2,000. I get this for free from concentrating in a thin layer, okay? But I need this extra factor 20, basically, to get basically 2 rate equals 1, all right? But this heavy core instability, which is the one which I'm interested in, happens for just an increase of order unity, maybe 20–50%, right? All right? So whereas gravitational instability requires roughly maybe closer to order of magnitude increase in order to be unstable. So hence the claim is that the heavy core instability will either destroy the vortex or at the very least will mix up the dust. All right? And this prevents dust buildup in vortex cores, basically. All right? Hence, vortices should not be regions where planetesimals can form. Right? So just to give a brief summary, because I'm basically out of time, imminent stages is hard to solve. Right? You can solve it if you have streaming instability or fidelity enhancement or vortex concentration. Right? But if you have vortex concentration, they will become generically unstable to the heavy core instability before the dust layer can undergo gravitational instability. Simply because the requirement for the heavy core instability is much less stringent than the requirements for basically gravitational instability. I haven't talked anything about nonlinear evolution because all I can do here is linear theory, all right? But it is likely that heavy core instability reduces the efficiency of vortex concentration. And there are many effects unexplored, but that will be some work in the future. Thank you.